Yes. Okay, so today we're going to do logarithmic functions. This is the last lesson of the unit. So next class we'll review, and then we'll have the test. So for us, that'll be on Wednesday. Okay. So the objectives. First, we're going to have, well, now that we learned about logarithms, we can do this first one, which is convert between the logarithmic and exponential forms of an equation. And then we're going to do pretty much like what we just did with exponentials. We should be able to recognize the graph of a log function and then transform it, move it around. Describe restricted domains and ranges. It will also have an asymptote. And behavior, not so much. I probably should have taken that one off. So a logarithm is another way to express an exponential relationship. So y equals b to the x, which is something we did in the last lesson, could be written, using logarithm notation, log base b of y equals x. Right, so notice that the b is the base of the exponential, is also the base of the logarithm. The exponent for the exponential is actually what the logarithm equals. So actually logarithms are exponents. So logarithms were invented in the early 1600s by a guy named John Napier. And their immediate impact was to simplify calculations. For example, like if you had to multiply really big numbers, that was not a very easy thing to do back then, right? They didn't have calculators, they didn't have computers. I mean, you could imagine somebody sitting around trying to do all this stuff longhand all the time. But by converting these numbers to their exponents with respect to a given base, the exponents are the logarithms, then you simplify the calculation. Like, for example, if my first big number, whatever it is, I could write it as some base, some number raised to a power. And then I could represent the other number as, the same base raised to a different power. Then I can use the properties of exponents to multiply those two numbers. I just have to add the exponents. And so that turns multiplication, which could be a longer, harder process, into addition, which should be pretty easy. So that was the first thing that they did when they had logarithms. It turns multiplication into addition. You don't need to copy all that. It's just a historical tidbit. So this is what we used to have to do. I'm saying, like, when I was in high school, this is the way we did math. We didn't have calculators yet. They were just coming out with 4-function calculators, and they were big. They were like 3 times the size of these things here, and they could do add, subtract, multiply, and divide. That's it. Right? They didn't have a logarithm button on it or anything. So basically, this one is base 10. So what these numbers are, this is just 2 pages of it, right? But these are all, what would the exponent be for all these values? You see on the left margin, it goes from 1 up till, I think I cut it off at, it's 5.4. But then you got on the top 2, so it's like, if I wanted to do 5.49 or 8, it's over here. There's the exponent, 10 to the 0.7388 or whatever it says. Right? That's how you would convert things to their logarithm. So then you could just add the logarithms. This is a little zoomed in shot of it. So you would do something like this. You'd say 135,000, I want to square that. Right? That's not a really big number, but it's a big number. I would take that, I would say, okay, well that's 1.3, that's 1.35 times 10 to the 5th. Turn it into scientific notation, and then you're going to square it, right? Now, the 1.35 times 1.35, you could look up 1.35 has an would be as an exponent, that is 0.1303, right? That's 10 to the 0.1303 times 10 to the 5th squared. So ultimately you're going to end up multiplying, or adding 0.1303 plus 0.1303. 10 to the 5th squared is 10 to the 10th. 0.1303 plus 0.1303 would be 0.2606, which you could see that would be like in between these two values here. So it would be somewhere in between 1.82 and 1.83. And we would actually have to make a proportion to figure out exactly, where should it be. But, that's the way things were done in those days. Now there's two, when it comes to the bases, whatever the bases are, okay, I'll get to that in the next slide. In those years, if you imagine when those years were, right, in the early 1600s, that's when they were first starting to do a lot of this important work with the orbit of the planets, right, and looking at the sun and stars and all that. Copernicus had come out in the mid 1500s. Galileo came along in the early 1600s, about the same time that this happened. He didn't invent telescopes, but he's the one, he made a telescope, and he looked at the moons of Jupiter. He could clearly see that they weren't going around the Earth, they were going around Jupiter. So, which is all the more reason to say, okay, it's time to get on board with the Copernicus way of thinking about this, which is the sun is not going around the Earth, everything does not go around the Earth, we're actually going around the sun. So they started actually doing a lot of the observational work with these telescopes and doing calculations. But the calculations involved really big numbers, long distances, and logarithms were very, very helpful for that. Now, the one guy who's given the most credit for doing some of these calculations, he actually came along a little bit before this, so he did all of his without the benefit of logarithms. But it was long and hard work. He's the guy, Kepler. He's the guy who said that our orbit around the sun, it's not a circle. It's really close to a circle. It's so close to a circle that if you saw it, you would say, well, that's a circle. But it's not a circle. It's an ellipse. And he did that, doing these longhand calculations. But anyways, logarithms came along at that time, and it did help. It helped to facilitate a lot of the work, astronomy work that was being done at that time. Okay, so the bases that we use for logarithms, log base b of x, the two that are the most important are log base 10, that I showed you the table of, which if you're dealing with log base 10, then you actually don't write the 10. If you just see log x, that means log base 10. If you look at your calculator, I think I can get it over here and you could see everything. You could see on the left column right there, log. It doesn't have a b on it for a base, so that's log base 10. The other one, that's called a common logarithm. I think it's fair to say that was the first logs that they came up with back in the 1600s. Okay, the other one is called the natural logarithm. And the natural logarithm has a base of an irrational number, right? Irrational numbers are numbers like unresolved square roots, square root of 5, square root of 3, or it could be pi, which you also have studied enough to know. Pi is this decimal number that never terminates and never repeats. Well, that's what E does also. And the value is about 2.71828 ... keeps going. So if you have a base of that letter E, then that's called natural log, and you write that with ln, right? That's not an in, that's a ln. And again, if you go to your calculator, right underneath the log button, log, says ln. That's what that is, natural log. You know, if you're doing work in science, it says log, it's ln. It's not log base 10. It's always ln. Oh, okay. I mean, you know, when you get into calculus stuff, in calculus, you know, you do a lot of what you do is you find derivatives. Let me add another slide here. You do derivatives. So like if I say I have a function which is f of x equals x squared, then the derivative of f of x is 2x. Okay, it's like one lesser degree. If I find the derivative of x to the third, I should say f prime. To make a derivative, you do a little prime. It's 3x squared. I mean, you're doing one, you're getting a polynomial. In the end, you're getting a polynomial. In fact, if I do f of x equals x, then f prime of x, the derivative, equals 1, because it keeps going down 1 degree, right? But notice what you get if you say that if the function equals, if the function equals ln of x, the derivative equals 1 over x. And so it kind of like jumps from one kind of function to a completely something different, which is kind of interesting. Okay, now, another thing I was going to show you. I think I might have actually said some of this to you guys before, because I said it to some class. And again, for the video, nobody will see this, but if you can kind of see the shape right here, it kind of looks like a U. You know, if I said, what does it look like? You say it kind of looks like a parabola. It's not a parabola. Remember, parabola might look like a U, but it's got a very precise shape. A parabola, again, if you shine in parallel rays into the back of it, everything reflects to a focal point in the middle, which is why your satellite dishes are parabolic dishes. That is not that shape. That wouldn't work if you shine things into the back of this. This is actually a necklace around a woman's neck, let's say. And back in the days, like 1600s, when they were first doing analytic geometry, because there was, for the first time they had the coordinate axis, right, x and y's, and they could start to describe, relationships and functions, and shapes by coming up with equations. For some reason, that was something that they wanted to study. What is exactly the shape of this necklace? And now I'll draw it here. And the guy who solved it, it was rather a competition, and the guy who solved it was named Bernoulli. And this ends up being the function. F of x equals e to the x. Now, would e to the x be exponential growth or decay? Growth. If e is 2.7 something, it's going to be exponential growth. Plus 1 over e to the x, which would be decay, divided by 2. So in fact, this shape, it's the average of this and this. And you put all that together and you get that shape right there. So it's the average of exponential growth and decay, with the base of the exponential being the base of the natural logarithm, e. Okay, now that may sound interesting, but who cares? But if you take that shape and you flip it upside down, then what does it look like? Yeah, it looks like an arch, right? It's called a catenary arch. Catenary arch. And that shape is like singularly self-reinforcing. That the way that this arch, everything is stacked on top of each other, is like the way it goes up and over is just so that it can support the most weight possible when you get the whole thing constructed. So something like the St. Louis Arch, that's why they use that kind of shape. If you go into like some of these, they gave a few examples of buildings and cathedrals and things like that, and you see this kind of curved shape in the ceilings like that. That's the shape. Because, architects know that as a shape that is singularly strong. So you definitely want to use it and stuff. But, what is it? It's using exponential growth and exponential decay models, which we just studied, and using the base, which is that base of the natural logarithm, e. So I think that's kind of interesting. Okay, another way that e comes up is compound interest formula. Remember the parts of the compound interest formula. One of the pieces was this n, and the n represents how many times per year are you compounding. And as the number of compoundings go up, the amount of money you're going to have also goes up. But it turns out that it's not without limit. It's not like you could just keep going and going and going, and it'll just keep going infinitely high. There is a limiting factor, which is something you get if you do what's called continuous compounding, which would seem like it's not even like enough to say we're going to compound every second, which is it's kind of ridiculous to even think of it. But it's even more than that. It's just you're in a continual state of compounding. When you do that, then this formula turns into this formula right there, right? That the amount you have is the principal times e to the RT. So the limit as you let the number of compoundings go to infinity, then this thing here turns into this thing here. So that's another place you see the e come up. They say it's the base of the natural logarithm, but it comes up in lots of places that are just really, really interesting how that can work that way. Okay. So the first objective with the exponentials and logarithms on both slides said we got to be able to convert from one notation to the other. So I'm going to do a few examples of this, and then you'll do a slide of it too. So again, if b to the x equals y, that means log base b of y equals x. So let's convert 2 to the third equals 8 into a logarithm. What will be the base of the logarithm? 2, right? The base of the exponential is the base of the logarithm. Okay? Now, what goes in the logarithm and what is the logarithm equal to? Remember, the logarithm is a exponent, right? So we have to say the logarithm is going to equal 3. So what goes inside is the 8. If you're not looking at the equals 3, if you just say, what is log base 2 of 8? In your mind, you're supposed to be saying, what power would I raise 2 to get 8? And the answer is 3. Okay, let's do this one. Log base 4 of 1 equals 0. Let's convert that one to an exponential. What would be the base of the exponential? 4. Okay, what would be the exponent? 0, right? And that means it equals 1. So 4 to the 0 equals 1 is a property that we know, properties of exponents. Anything to the 0 power equals 1. Well, it's the same thing to say that the log of any base of 1 equals 0. Right? The log of any base of 1 equals 0. Okay, let's convert 12 to the first equals 12 is kind of common sense, right? Anything to the first power equals itself. Okay, convert that to a logarithm. What's the base? 12, okay? And what goes inside the logarithm? 12 equals 1. So if you take the logarithm of something with a matching base, it equals 1. So we could say more generally, log base b of b equals 1. As long as you match those two, it's going to equal 1. Okay, how about this last one? Log base 1/4 of 4 equals -1. What's the base of the exponential? 1/4, right? And what is the exponent? negative 1 equals 4. Which makes sense, right? We know when you raise to a negative exponent, that just flips it. So then you get 4 equals 4. Okay, so try to do these ones here. You know, the exponentials, turn them into logarithms. The logarithms, turn them into exponentials. Okay, 3 to the 4th is 81. What's the logarithmic representation of that? Log what base? 3 of equals 4, right? Log base 7 of 7 equals 1. 7 to the 1st equals 7, right? 14 to the 0 equals 1. Log base 14 of 1 equals 0. Remember, the log of 1, just regardless of the base, equals 0 all the time. And the last one, 1/2 to the negative 5 equals 32. Good. Okay, so again, that's like the first knowledge and skill from the SOLs that we're supposed to have. Okay. Next, we should know how to use the calculator to evaluate logarithms. So we already talked about this, but on the left side, the LOG button right there, that's the log base 10, common logarithm. The LN button underneath it, that's the natural log button. And then if you want to do a logarithm of any other base, in fact, this is relatively new, like within the last few years, that now that function is in the calculator. We used to do a change of base formulas, but now it's actually in the calculator. If you go to your calculator and hit the math button, and then you scroll all the way to the bottom, and it's at the letter A, it says log base. And if you look on the screen, you're going to get this thing here. You can fill in whatever base you want right there, and then put whatever you're taking the logarithm, the argument there. So those are your 3 options for taking logarithms. All right, common log and natural log are right on the front. The log of any base is inside. Do you all find it? Anybody need help finding it? There's another thing you can find useful eventually, another place to find the same thing. And actually there's a few other things that we find there too. Let me get out of this. 2nd plus 712. If you do alpha window, it brings up a few functions that are useful. Okay, I think yours, because it's a newer calculator, it's got 3 additional ones on the bottom that didn't used to have there. But it definitely has the number 5 option is log base. It's another place you could find it. It also has absolute value right at the top, which is one we use a fair amount. And we will use the number 2 in the 2nd semester, the summation notation. The 3 and the 4, those are calculus things. Okay, so if we know where all the logarithms are, then let's try, just try to do them, get the decimal values. Make sure you know how to use them. Okay, somebody give me what's log 8? 0.03. Okay, I'll just ... Okay, makes sense. I mean, it's log base 10. You know that 10 to the 1st is 10. So 8, it should be a little bit less than that. So 0.903 sounds about right. Okay, how about the natural log of 0.3? Negative 1, 0.2, 0, ... Okay. How about log base 1/5 of 125? Exactly negative 3, right? Now, if you look in the book, they have some examples like how do you evaluate something like that? And without a log base function, what we would do is like this. We would set it equal to x. That's what we're trying to solve for. And then we would convert it to an exponential, right? The exponential then would be 1/5 to the x equals 125. and then you would solve that. But again, you got a log base button, so you really don't need that. Okay, so the next, and this relates a little bit to what we're going to have on the quiz here. How do we find the inverse of a function? We're going to try to find the inverse of a logarithm. Okay, well first, you got to replace the f of x with a y, right? So first do that. So y equals log base b of x. Okay, then we switch the x and the y. X equals log base b of y. Okay, then what's the next step? Solve for y, right? But the y is inside this logarithm function. And I can't just like divide both sides by log. So instead, let's convert that to an exponential. Right? What would be the exponential? What would be the base of the exponential? B. Okay, what would be the exponent? X. And so what does all that equal? Y. So by converting it to an exponential, we did solve for y. Right? That accomplished the trick. So actually f minus 1 of x equals b to the x. Okay, so that tells you that logarithms are inverses of exponentials, which is useful for us here, okay? So the inverse of a logarithm is an exponential. The inverse of an exponential is a logarithm. So here's the graphs. Okay, I've got y equals 2 to the x is the exponential. Log y equals log base 2 of x is the logarithm. Those are inverses of each other. And I've graphed them using the GeoGebra software. So you can see the exponential is the green line right here, and the logarithm is right here. So remember the characteristics of the exponential. The domain is all real numbers. The range is y greater than 0. There's an asymptote along the x-axis, y equals 0. And there's a y-intercept at 0, 1. Okay. But now, if all you're going to do now is switch the x's and the y's, because that is what you do for inverses, then that means our domain now has to be x's greater than 0. Right? Because the range of the exponential was y was greater than 0, then the domain has to be x greater than 0. The range of a logarithm is all real numbers, because the domain of the exponential was all real numbers. Right? Whereas the exponential had an asymptote on the x-axis, the logarithm has an asymptote, sorry. The logarithm as an asymptote on the y-axis, so it's x equals 0. And again, the exponential had a y-intercept of 0, 1. That means the logarithm has a x-intercept of 1, 0. So there is an asymptote right there. And then what is that line going to the middle of those two again? It's what this is y equals x, right? Just getting across that point that a function and its inverse are reflections across the line y equals x. And it definitely looks like it on this one. So we should understand the base, again, just like with an exponential, whatever the base is, that's part of the parent function. So log base 2 of x is a parent function. Log base 4 of x would be different. Log base 6 would be a different parent function. But they would all have, the basic characteristics would all be the same. Okay, now let's figure out how do we graph when using transformational approach, so to speak. So sketch the graph, include and label the asymptotes, state the domain and the range. Okay, what's going to be the effect of this plus 3 inside? Left. What is the effect of a plus 1 outside the function? Up 1. So which one of those two is going to move the asymptote? Try again. Left 3, right? If you're looking at a vertical line, right, going up a vertical line, moving up and down doesn't change position, but moving left and right it does. So when we graph, the first thing you got to do is get the asymptote in the right place. So let me do that. Solid line, black. We're going to go left 3, so maybe I'll put it about right there and about right there. And tick marks. Left 3, 2, 3, 2. Hopefully that'll be enough. Then go back and do my asymptote. Should be about right there. So include and label the asymptote. X equals -3. Okay, now we need a couple values, and you could do this by putting it in the calculator and then just looking to the table of values. I mean, one thing you could do is the parent function had an x-intercept at 1, 0. So we could apply these two shifts, right? It goes left 3, 1, 2, 3, up 1. So there has to be a point right there. So that looks like it's got the point -2, +1. Does that look right? Left 2, up 1. Okay, that's good. And then if you want to find another one, okay, I'm going to walk away from the microphone. We know that if you're taking the logarithm of the base, and you match the base to what you're taking the logarithm of, then it equals 1. Right? We saw that in our conversions a couple of times. What would I have to substitute here for x so that it matches the base? So that this value is the same as the base. -1, right? So that if I put in x equals -1, then log base 2 of 2 equals 1. And 1 plus 1 is 2. So if I put in -1, then I should get a value of +2. Again, we saw this, and I put that on the side. If you have the log base b of b, that equals 1. So if we substitute -1 here, now we got the log base 2 of 2. So the whole thing you can replace with a 1. So it makes the calculation easier. So now we can put in -1, 2. And then we know what the shape of the graph is supposed to look like. It's supposed to hug the asymptote and then kind of veer off, but it's not like going up exponentially, right? It's not flattening out, but it's not going up very fast. Something like that. Okay, now, what is the domain? Right, the domain is x is greater than -3. What is the range? All real numbers, right? Okay, now before we go to the next slide, with your calculator, let's put this in the calculator to see what the graph looks like if you do it there. Because it's something you have to see, right? Y equals, and now we're going to use the log base function. So y equals, where we're second quit, y equals. So alpha window 5, I want to put in 2, then arrow up, put in x plus 3, then get out of that parentheses and put in a plus 1. Okay, then hit graph. Now, if your calculator is not showing the graph like right in the middle like you want it to, zoom 6. Zoom 6 is zoom standard. That gets you back to the middle of the graph. Now, notice what that graph on the calculator looks like. Right? It has the line like it's into quadrant 3 and then it just stops. But it doesn't stop. That's just the calculator. Right? You got to understand that this graph that we drew is better because it actually keeps going along the vertical asymptote. But the calculator, once a line gets really close to vertical, it just stops drawing it, which is not good, but that's what it does. Okay, so like if you have to graph it on a test, and you give me a graph that looks like this, it tells me that you don't really understand the graph, so you're just like copying the screen, and you're getting it wrong. So you got to know more than the calculator on this particular function because it always makes it look goofy. And the other thing is, notice how it's going off into the first quadrant here. You know, if you're usually when they ask you for asymptotes, they don't tell you vertical versus horizontal. They're just going to say, what are the asymptotes? And so you don't want to look at that and say, oh, it looks like there's a horizontal asymptote. There is no horizontal asymptote. It may look like it's leveling off, but it's not. Remember, the range is all real numbers, no matter what. So don't be fooled by the calculator's graph of logarithm. Okay, so one more, which is for you. Try, sketch the graph, include and label the asymptote, state the domain and the range. So where do I got to draw the asymptote? -1, right? It went 1 to the left, so I got to draw an asymptote at x equals -1. So about right there. And then, of course, don't forget to label it. X equals -1. Okay, then for a couple points, again, I can start with the x-intercept of 1, 0. Has been moved 1 to the left and 2 down. So if I started here, I went 1 to the left and 2 down, it looks like 0, -2. And then what value could I plug in for x there so that I have log base 4 of 4? 3, right? If I put in a 3 there, then I'm going to get log base 4 of 4, which equals 1. Right? The log, if you match the base with what you're taking the logarithm of, it's 1. And 1 minus 2 is -1. So plot those 2 points. 3, -1. And then with those, sketch in the graph. And the domain is x is greater than -1. The range, all reals. So now we know there's 3 restrictions to domain. Okay, one is can't divide by 0. One is can't take the even root, square root, of a negative number. And now we know you can't take the logarithm of 0 or negative numbers. Okay, those are the 3 restrictions to domain that we've got. And the only other ones that come up are in trigonometry. So let's see. That was the end. And that's the homework.